we now come to Chapter 7. This is going to be our last chapter over the probability chapters. So we've had chapters 5, 6, and 7 outlining probability theory. Chapter 7 is going to focus on continuous probability distributions. Remember, Chapter 6 was discrete probability distributions. Chapter 7, continuous. All right, in this chapter, we are going to describe the uniform probability distribution and use it to calculate probabilities. Our second objective will be to describe the characteristics of a normal probability distribution. And our third and final objective, describe the standard normal probability distribution and use it to calculate probabilities. All right, the uniform distribution is perhaps the simplest distribution for a continuous random variable. The distribution is rectangular in shape and is defined by a minimum. So it's rectangular in shape, and it is defined as a minimum and maximum value. Let's just color that in. The uniform distribution. The mean and the standard deviation of the uniform distribution. If we know the minimum and maximum value, we can define the probability function. If we know these values, we can calculate the mean, the variance, and the standard deviation of the distribution. So the uniform distribution, we said, was what? Our probability would be 1 over B minus A. We just define B minus A, your maximum and minimum values. The mean of the uniform distribution is A plus B divided by 2. Minimum to maximum divided by 2. And the standard deviation, we're going to go ahead and say we're going to take the square root what are we going to divide that by?
12.
So here are our 3 formulas. Okay, let's look at an example. Southwest Arizona State provides bus service to students. On weekdays, a bus arrives at the North Main Street and College Drive stop every 30 minutes between 6 a.m. and 11 p.m. Students arrive at the bus stop at random times. The time that a student waits is uniformly distributed from 0 to 30 minutes. Now let's picture this here. Students are at a bus stop, waiting on a bus to come. Bus is going to arrive every 30 minutes from 6 a.m. to 10 p.m. Students are going to arrive at the bus stop at various times to catch the bus. And the time that a student waits follows a uniform distribution of 0 to 30 minutes. Okay. How are we going to graph this distribution? All right, so let's look at it right here. In this case, we'll assign 0 to 30 minutes. And what's the probability up here?
Looking on the side, I got 0 to 0.060.
Well, if we want to call this, if we would define that all the way up, our probability, our shaded area is going to be 1/3 of 0.33. Number 2, show that the area of this distribution is 1. That would be important right now to understand real quick, how do we solve for area?
Area is length times width, isn't it? Length times width. Area. This says height times base.
Yeah, I'm dividing height times base. Okay, so what is our height times base?
Will be 1 divided by 30 minus 0.
30 minus 0. So the area, 1 divided by what?
30 minus 0.
30 minus 0. Multiplied by
30 minus
30
0.
minus 0.
Just follow the example in the book. All right, so this was problem 1. Here we're at 2. Number 3. Here's the good stuff. How long will a student typically have to wait for a bus?
30 minutes.
In other words, what's the mean waiting time? Let's apply this for
15 minutes.
How are we getting this?
A plus B, so 0 plus 30.
A plus B.
Yes.
A divided by 2. Number 4. What's the probability that a student will have to wait more than 25 minutes?
So the standard deviation would equal B minus A squared divided by 12. The square root of.
You're wanting number 4, which is the area. Take the area within the distribution for interval 25 and 30 represents particular probability.
So
So
what's the
area.
You want to look at what's the probability that someone would have to wait within this range of 25 to 30 minutes.
So you're going to take 1 over 30 minus 0.
So we're going to look at more than 25 minutes. So we're looking at, I'm just going to say the probability between 25 and 30 minutes is equal to, let's come right back up here. So what part of this area is shaded? So we're looking at just this area that would be right in here.
So that would be like, you take, that's how you get the 5 is the 25 minus 30.
Correct.
Yeah. Okay. So it's going to be 0.1667.
All right, now the last, let's look at this one again. What's the probability a student will wait between 10 and 20 minutes? So now what's the probability that we are within 10 and 20 minutes?
So you're still going to do the 1 over 30 minus 0. And that's going to be times 10. Because that would be the middle between 10 and
Our
20.
10 here is shaded. And what does that give me?
0.333.
Repeating?
Yes.
0.333. Okay. Moving right along to a normal probability distribution. What are the characteristics that we are going to take on? What's the shape of it?
It's going to be a curve. Bell.
A bell-shaped curve. What's that mean?
It has a single peak in the center of the distribution.
Single peak in the middle.
The mean, median, and mode are equal.
The mean, median, and mode are equal.
And they're all located in the center.
And they're all located in the center. Now remember, we say it's bell-shaped, and that peak is going to be symmetrical. So that means if we divide it in half, we have 2 equal parts. As we get closer to the x-axis, it's never going to touch it. Asymptotic. It's going to go, it's never going to touch it. And my best rendition, let's draw it right here. Okay, if this is my x-axis, let's draw it bigger than this. Let's get it big. Okay, so x-axis. Here we've got the mean, the median, and the mode. Its distribution is symmetrical around the mean. These are two equal parts. As the tails come down to the right and left, they never touch the x-axis. Instead, we assume that they would be continuous. They're going to run continuously in each direction. Whereas we say here is the mean. Any spread around this mean is going to be measured by the standard deviation. The probability of falling under this curve. All area under this curve is defined as what value? 1. Everything is encompassed in that curve. So if everything under the curve, what area under the curve is this? To the right of the mean. And what area is to the left?
0.5.
We just described a normal distribution. Okay, now, just because it takes on this shape, you know, we could also have it can take on a variety of different shapes. All of these are normal distributions. And what I did here was I changed the height, yes, but I still created these same rules. Now the standard normal distribution is called what?
Z value.
The Z value. Tell me a little bit about the Z value.
The signed distance between a selected value designated x and the mean divided by the standard deviation.
Okay, so the Z value on the marker is a little darker, is equal to divided by what? The standard deviation. Lids are not matching up to the markers. Okay, we also call this a Z distribution. Okay, so we're going to call this the Z distribution. And what we are going to reference is Appendix B3. So again, here is my we said this was 0.5 and this was 0.5. So when we calculate our Z score, we're going to be looking at What's the probability of falling over here? Black does not want to work. All right, so this is going to illustrate what we're doing. Okay. The empirical rule. What do we say? When z is equal to 1, the table's value is 0.3413 times 2. Okay, so in this example, and we're going to say 0, 1, 2, 3. And remember, what's at this level right here?
Mean.
The mean. And we're going to be measuring distributions out from around the mean. So when z is equal to 1, we get what? 0.6826. I want to illustrate this before I show you Appendix B3. When z is equal to 2, 0.9544. When z is equal to 3, 0.9974. Here is our z. So from when z is equal to 1, we're in this area. Calculating a z of 2 puts me in this area. The calculation of 3 is going to pretty much put everything under the curve. Okay, so the idea is a z of 1, you're going to cover everything under the curve, is equal to 1. When you calculate z of 1, know that you've got 68% of the data under the curve. A z of 2, 95%. And a z of 3, so one standard deviation removed is going to encompass 68% of the data. 2 standard deviations outside of the mean, 95%. And 3 standard deviations, 99.
And you're only talking about the curve. Are we talking about the altitude or just the curve?
Remember, with sampling, let's go back to our sampling rule. And when you're sampling from a population, you're never going to have 100%. You don't expect a 100% match. The idea is we're sampling to tell us something about that population. And yes, we need some type of confidence on how likely are we getting a true interpretation of that population.
Okay.
And what this should suggest is if we're willing to accept greater standard deviation, we can expect a higher probability of having 100% data. All right, let's look at an example. I think examples always tell a good story.
And on that, we don't round up, correct? So that would not be rounded up to 100%.
No, because you're never going to hit 100%.
Okay.
Okay, let's look at weekly incomes. Weekly incomes of shift foreman in the glass industry follows a normal, here's the words we're looking for, a normal probability distribution. And let's assume that the mean is 1,000 and the standard deviation is 100. Okay, so dries here a little bit. You following with me?
Where's your example at?
I think it's the one on 218, page 218. That one.
All right, so what was our formula for Z again?
Z is
X minus.
X minus mu over the standard deviation.
Okay. So, weekly incomes of shift foreman in the glass industry follows a normal probability distribution with a mean of 1,000 and a standard deviation of 100. So we know that the, over here, the mean is 1,000 and the standard deviation is 100. What is the Z value for income? Let's call it X, of a foreman who earns $1,100 per week for a foreman who earns $900 a week. All right, so what's the Z value for a foreman who earns $1,100 per week? What? 1,000
Minus 1,000 divided by 100.
divided by 100 gives me
1.
1. Now, when X equals 900, minus 1.
Yes.
Okay, then what did we just do? Going and looking at this normal distribution. So what's the likelihood of a foreman's income being between 1,000 and 100? So if we're going to look at this as income dollars, what's the likelihood of coming between $1,000 and $100? Okay, so we calculated 1. Now let's go to our okay, so I'm in appendix B3, areas under the normal curve. And what did we just calculate? A Z-score of 1.
1.
So let's come out here and let's look at this. So 0.3413. You with me?
Mhm.
So we can assign the likelihood of coming within this, the probability of falling within this area is 0.3413. So putting this and interpreting this, you have a 34% probability of selecting a foreman whose income would fall between $1,000 and $100 per week. Remember, a continuous, unlike a discrete used for counting, continuous, usually within a range of measurement, defined by minimum and maximum values. So the likelihood of selecting a foreman whose income would be between $1,000 and $1,100, 34%. Now the book will give you examples. Be sure you look at I prefer you to try to tackle it this way if you want to see it computed using technology. Excel, Microsoft Excel will calculate this for you. Reference the Excel tutorials that are inside Blackboard. Okay, now let's look at this example. And what's the probability of selecting a shift foreman whose income is between $790 and $1,000? So 790 and 1,000. Solve this for me.
2.1.
So what we're looking at here, mean is at 1,000. So now let's say 790. So now I'm looking to the left of the curve, to the left of the mean. What did we calculate Z for?
Should be a negative then, wouldn't it? What's
790 minus 1,000 divided by 100 is 2.1, I think.
Negative 2.1. So let's look at our Z score. Well, I'm jumping straight from the science to random numbers. What's wrong? Then on page 732.
Yeah.
Here we go. Didn't like to sort. So what did we calculate? Our z-score was negative 2.1.
Mhm.
So 2.1. Right here. I'm not going to put a reference right now. Watch this. So we say 0.4821. So we're at 0.4821. Now, out of curiosity, what's the probability that I would find and select a foreman whose income was greater than $1,100? So in this range. So what we just said was this was equal to 0.3413. What's the probability that I pull someone over into this range? And our probability is 0.4821, 48%, that I would select a foreman whose income was between $790 and $1,000. What's the probability that I would select someone whose income is less than $790? What's the probability that I'm out in here? One of the characteristics of the bell curve, what did we say was the surface area under the curve? What was it equal to?
1.
1. What's it equal to on each side?
0.5.
Mhm.
If right here we say that 0.3413 will fall between 1,000 and 1,100, then what must greater than 1,100 equal?
So we would subtract 0.5. Yeah.
And over here,
Okay.
So the greater would be, above 1,100 would be 0.1587. And it's 0.0179.
point what?
0.0179.
0.179. So if the question would have been asked, what's the likelihood of selecting a foreman whose income is greater than $1,100?
Mhm.
This is how we could solve for it. What's the probability of selecting a foreman whose income is less than $790? This is how we would solve for it. You good?
Yep.
Yes.
We hit all of our objectives?
I think so. Let me look. Yep.